Hi everyone. Hope everyone is doing well, and welcome everyone to today's session on optimizing machine learning models and model level evaluation metrics. We'll be talking a bit more about hyperparameter tuning. We'll talk a bit more about model evaluation metrics and also hyperparameter tuning and a bunch of other concepts. And today we have with us Raviraj, who is a passionate data science geek and also a software developer at Skellam AI. And not just that, he keeps contributing to the community during his free time, and he has contributed to our last previous boot camps, data science boot camp, and also deep learning boot camp, where he also delivered one of the sessions. And with that, I'll probably let Raviraj take over the session. Ravi, please go ahead and yeah, maybe I think you need to unmute yourself. Yeah.
Hey, hi Chanukya. Thanks for the kind intro. So, hi everyone. Today's agenda is we'll discuss about model evaluation and hyperparameter tuning, and also we'll talk about performance metrics, how to evaluate a model, and how to compare a model with other good models. And so that will help you in deciding how good the model is. So let's start. So why do we evaluate performance? So I already told we evaluate performance for a model to check how good that model is. And also, if you want to compare your model performance with another model performance, you need to know some metric, right? You need to have a metric for the model to compare it with other models to see which one is good. And also, so the performance metric on model will tell how good that model is performing on a new data. So that's why we need performance metrics. And also, as you know, there are two types of models: classification models and regression models. And then there will be different metrics for both. For classification, you will have different metric, and regression, you will have a different metric. And why do we need different metrics for both of them? Because in general, classification will have discrete variables. Like it can have a class like positive and negative. It can have classes like dog, cat, like different types of animals. Each animal will be assigned a number, and then those numbers are discrete variables. And when it comes to regression, you will predict a single variable like a person's age or a company's income. So those kind of attributes you'll be predicting based on few input features, right? And so the first classification metric is accuracy. And by the name, what you can understand is how accurate the model is. So how do you calculate accuracy? So accuracy is number of correct predictions over number of all predictions. Like suppose if you are if you have prepared a model, and then if you want to calculate accuracy for that, you will just send test data and then calculate few predictions. Suppose if test data has 100 samples, you send those 100 samples to the model, and then if 90 samples are correct, accuracy will be 90%, like that. So let's take an example, small example. So these are the actual labels of the data. So here we are trying to segregate yellow balls with pink balls. So there are 4 yellow balls and 2 pink balls. So these are actual labels. And imagine that you have a model at hand, and then that model has predicted the below labels. So this one is yellow, right? And the model predicted it as pink. And the second one is yellow, and the model is predicted as yellow. So like that, for each sample data, and it is giving some prediction. So here you can see how many are correct and how many are wrong. So here, if you can see, there are 4 data points where model has predicted correctly, and for yellow it is predicted as pink, and for pink it predicted as yellow. So how do you calculate accuracy? Based on the formula given above. So it's like we have 6 data points, and then 4 of them are predicted correctly. So that will be 4/6 multiplied by 100, right? So that is accuracy. So here you can see that is accuracy. Accuracy predicted is 4 by 6 multiplied by 100. That's the ratio. That is 66.7%. And so, so is accuracy alone enough to decide whether a model is good? No, right? Because one metric with one metric you can't just tell whether a model is good and then it's working well with the new data and test data. So what you can do is you can take a small example like credit card fraud detection. So when you have fraud detection data, 99% of the time or 98 or 99% of the time model will the transaction will be valid. Only 1 or 2% fraud transactions will be there, right? Only one or two transactions will be fraud. Even if you take 1,000 transactions, only like very few will be fraud. So in that case there is a heavy class imbalance, right? So you have when you take the training data 909 999, like if you take 1,000 samples, 99% of the data will be 99% of the data will be correct, and then like other 1% only will be fraudulent. So in that case, what if you just send all normal transactions to model? It gives 100% accuracy. So you just can't tell, like even if you get 100% accuracy, that model is not good in detecting fraud transactions because there is a heavy class imbalance over there, right? And also we'll take a small example with this similar example, the same one which we have discussed before. So here we have actual labels like this, yellow and pink, right? And the model has predicted this. So we have taken a baseline model. A baseline model is something which is very basic model, and then like we'll create models on top of those that baseline model, and then we'll take that as reference, and then we'll try to improve the model. So here my model is nothing but uh, it just selects the majority class. So in this, what is the majority class? In these actual labels, majority class is yellow, right? So whatever the data point you give, it just gives yellow because majority class is yellow. Suppose if I have 4 pink balls here and 2 yellow balls, and then all predicted labels would be pink. So in this case, what is the accuracy? Accuracy is the same again because 4 data points has the correct labels, correct predicted labels, and 2 are wrong. So that will be 66.7. And then this is like not better than the previous model, right? Which is the previous model is our model, and this one is baseline model. So this one is not useful for us. So let's look at some other metrics apart from accuracy. So what do? Like we try to create a confusion matrix. So a confusion matrix is something which gives us info about what which gives us info about true positives, which are like the labels which are yellow and predicted as yellow. So it gives information about balls which are yellow, which are actually yellow and predicted as yellow. That is one type. Which are actually pink but predicted as yellow. That is another type. There are actually 4 types, right? Because there are 4 combinations. The ball can be yellow and it can be predicted as yellow, and the ball can be yellow and it can be predicted as pink. If it is pink, it can be predicted as pink and yellow. There will be 4 possibilities here, just because you have 2 classes. If you have more classes, you will have more possibilities like this. So this is the breakdown of 4 categories. So let's take 2 classes. Let's not call yellow or pink. Let's call one class as positive and other class as negative. So these are 4 categories. So one category is actually positive and predicted as positive. It's called true positive, and we also call it as TP. And another case is actually it is positive but predicted as negative. That is another case, false negative, which is falsely classified as negative. Since it is falsely classified as negative, it is actually positive. So even if you don't have this above information, by looking at false negative or true negative, you should be able to interpret what it actually is. So if you take true negative, it is truly negative. That means it is negative. If you take true positive, it is truly positive, that is positive. If you take false negative, it is falsely classified as negative. Since we are negating negation, that will be positive. Here false positive will be negative, actually it will be negative. So if you take this example, I told you like these are shorthands for false negative, true positive, false positive, and true positive. So here you have actual values on this side and predicted values on this side. So here if you see this one, this will be, this box here represents the actual positives predicted as positives, that is TP. So you can just create a matrix like this saying I have a positive class and then it is predicted as positive. That, so there are three values like that, and there are some actually negative labels but predicted as positive, there is one label like that. So here can you can, can we can we tell what is the accuracy? So you have the confusion matrix, so the accuracy will be the correct predictions over all predictions, right? So in this, what are correct predictions? So here if you see the breakdown, positive is predicted as positive and negative is predicted as negative, that is true positive and true negative. So these are, this first box here and fourth box here will be the correct predictions, and all the boxes will be, if you sum up all these boxes, that will be your total predictions. So what is the accuracy? Accuracy is 4 divided by 6, right? That is again 66.7. So what is our goal?
Hi,
Yeah.
Ravi. Can you please click on that hide thing? I mean, just beside stop screen. Yeah, yeah.
Okay.
And also, yeah.
Any questions so far, Chanakya?
Uh, yeah, no, so far. I think like maybe people are slightly confused about the class imbalance thing, but yeah, I think we can cover it. We can pick up the question a little later. But just sharing some context about class imbalance. Let's
Yeah,
say,
I'll actually do that in notebook if that's okay.
yeah, yeah,
Yeah.
we can do that later too. Okay,
Yeah.
or yeah,
So what is our goal here? Our goal is to increase the correct predictions and decrease the wrong predictions. So here what are correct predictions? True positive and true negative will be correct, and false positive and false negative are wrong. So our goal is to increase TP and TN, and increase as in like we need to maximize TP and TN for any model, and FP and FN should be as low as possible. Like we need to minimize those FP and FN. So let's look at another metric. This is another metric. So far we have covered accuracy and confusion matrix. So you have confusion matrix here, but you can't compare confusion matrices of two models just like that. So you need to understand this confusion matrix completely. So you can create a lot of metrics from this confusion matrix. So all these metrics here, sensitivity, and then like the metrics which we are going to discuss, all these metrics will be calculated from a single confusion matrix. So let's see what sensitivity is. So sensitivity is a model's ability to predict a positive label as positive. That's it. Suppose let's talk in norm in layman's language. So let's take an example. So sensitivity is telling a suppose if a patient visits a doctor and he has cancer, if the doctor says he has cancer, that will be like you so that will be sensitivity of the doctor, right? He's actually telling a positive cancer person that he's positive, right? If he says you don't have cancer, that person will have less sensitivity. So this sensitivity I'll explain in the notebook again. So maybe just let me know if you have any questions about sensitivity. Sensitivity is just that true positive rate as in like you have true positives here and then true positives over actual positives. So that is FP by FP plus TN. These are actual positives. So it's just the rate of true positives over actual positives. That's it. So I'll
Yeah.
explain. Yeah, tell
Yeah,
me,
Ravi.
Ramesh. Yeah.
Probably there is one question maybe we can try and address. I think people are not clear about. Can you please explain with example why accuracy is not a good metric? Right.
Okay.
Maybe
Yeah.
before we jump into the next slide, probably we can add some more light. Let's say, for example, in the case of why accuracy is not a good metric, right? So, for
Mm-hmm.
example, if there are 100 fraudulent transactions or 100 transactions on a credit card data, and in that 100 transactions it is likely that 99 transactions are not fraudulent and one transaction is fraud. So if we apply a model which is technically which is just saying that all the transactions that you input would be non-fraudulent, in such a case that in such a case accuracy may not be valid, right? So probably you can maybe add throw some light by showing an example that you already have in the notebook or somewhere. Okay, so I think that's where people are slightly confused.
And
Yeah.
there's another question about what exactly are classes. So I think that can also be covered at the moment.
Yeah.
Like, what are classes and what imbalance of classes are we actually talking about?
Okay. Yeah, I can cover that. First, I'll take the classes question. So basically, when you take a classification problem, so the idea of a classification model is to classify few things into different classes. Suppose if you have pictures of animals, and then out when you see a picture, suppose if you want to create a model which tells what animal it is by looking a picture of it, and when you send that picture to the model, it tells whether that picture is cat or dog. So, and in that case, you can assign class 0 to cat and class 1 to dog, and then when your model gives 0 or 1, you can just tell whether it is cat or dog. So those are classes. Like, classes can be anything, different kind of animals, and different kind of transactions, like fraudulent transaction or non-fraudulent transaction. Also, like, you can take fraudulent transaction as positive and non-fraudulent transaction as negative in this case, if you have binary classification. So these are two types of classifications, like binary and multi-class. In binary, you have only two classes, which are basically two labels, like yellow and pink. So when you look at this example, you have only two classes because there are only two colors. If you have three colors and then you have to predict the color of the ball, that will be a multi-class classification because you will be having three classes. So am I clear in this, Gunika, about the classes?
Yeah, that is clear. And
Okay.
about the imbalance in classes, for example, like if we have a lot of pictures of dogs and we have very few pictures of cats, so
Mhm.
what our model will do is if we only use accuracy as the metric, that it will simply say that all the pictures are dogs. And since it'll get a huge accuracy because most of the pictures will be of dogs, then it'll think that it is a good model. But actually, what it is doing is it is not correctly predicting the cats. So that is what we are targeting, that even if a class is in minority, we are able to predict it well. And that is why accuracy might not be well suited here.
So I can actually add some more to it. Suppose if you so you actually know we decide we actually divide the data into train and test in most of the cases. So train data will be used to train the model, and test data is used to evaluate the model. So when you train the model on some data and the model learns something, and then when you test that model with test data, what happens if entire majority class is in the test data and there's no minority class? Like, so suppose I'm actually creating a model to classify dogs and cats, right? I have few pictures, but in test data I have only pictures of dogs and I don't have pictures of cats. And then I just send the data, the pictures of all dogs to the model, and it says all dogs. So that will be your 100% accuracy. You have 100% accuracy, but the model has not learned anything about cats, right? So that's why when you have class imbalance, accuracy is not a good metric. I hope I'm clear,
Yeah, that is
Chanakya.
perfectly clear.
Okay, great. So let's move on. So sensitivity, and I'll explain all these metrics in the notebook if that's okay. So sensitivity is something I've already okay. Sensitivity is something which is called as true positive rate. So that is true positives over actual positives. TP by, when if you want to see actual positives, you just need to see here in the confusion matrix. Actual positives are this column here, TP plus FN, because this is falsely classified as negative, which is positive, and this is truly classified as positive, this is also positive. So TP plus F1. So sensitivity is how sensitive a model is towards the positives. That's it. And specificity. So sensitivity and specificity we don't generally use because these are statistical metrics rather than our programming data science. So sensitivity, you just don't need to focus that much on sensitivity, but you just need to know that sensitivity um, is the ability of a model to tell a positive as positive. That's it. Positive as positive means it can be anything. Sensitivity of a model for that dog and cat classifier is so if you take dog class, the ability of a model to detect a dog is sensitivity. Like how sensitive is that model in detecting dog is that so sensitivity will be there for each and every class, and also with specificity, because these are class specific metrics. And when you see
Also,
specific,
one very nice question around it, like how will you
Mhm.
define which one to be taken as positive and which class to be taken as negative? So, for example, in the cat and dog, what would be like which class should be assigned positive, and accordingly, the sensitivity and specificity might change because true positive upon true positive plus false negative.
yeah, but you actually have sensitivity for dog and sensitivity of cat as well. It actually depends on the user. Like you can have not only positive and negative here. You can have cat and dog here. You can just write cat and dog and cat and dog. And when you can actually take uh, anything a positive, cat can be taken as positive or negative. You just need that. It's just a notation to 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 explain things. But when you have like multi-class classification problem, the confusion matrix will be big, and then like it will have n by n matrix, and then in that n by n matrix each class will be having a sensitivity. Am I clear?
Yeah, that is clear.
Also specificity is a class related metric. Each class will be having specificity, like positive will have one specificity and negative will have one specificity. If you take dog and cat example, dog class will have one specificity and cat class will have one specificity. So here if you see, specificity is the ability of a model to predict negative as negative. That's it. There are like, you just need to remember these two sentences. Sensitivity is the ability to predict positive as positive, or like the ability to predict a dog as dog, the ability to predict a negative as negative, like the ability to predict a cat as cat, something like ability to predict true negatives, right? So that will be, yeah, in this case cat as cat. Yep. And precision. So we mostly use precision. Precision is like a positive predicted value. It's like true positives over predicted positives. Like how many true true predictions are there over overall predictions, overall predicted, yes. So that means true positives over predicted positives. So here if you see, true positives are TP and predicted positives are TP plus FP. So let me just show you this. There is a nice article in, so let's see what accuracy is here. So here if you see, accuracy is, you can just see TP and TN divided. The blue thing is numerator and the green is denominator. If you see, this is accuracy, and the formula for accuracy is TP plus TN over all these boxes. And if you see precision is something like true positives over predicted positives. These are predictions, right? So this is true positive over predicted positives. if you take sensitivity or recall, okay, we haven't discussed recall yet, so let me just go back quickly. So that's precision, and so this sensitivity is also called as recall. So that recall is the same as sensitivity, like how sensitive is the model to in detecting positives or positives, like it's true positives over actual positives. So if you see that visualization again, so this is recall. It's like true positives over actual positives. This, we are taking this row, the first row, because this is actual positive and this is actual negative. This is prediction positive and prediction negative. Out of all these rows and columns, we are actually taking the first box divided by the first row, which is true positives over actual positives. This can be a bit confusing for the first time, but when you start working on it, you will understand it. Okay, let's continue. And F1 score. And F1 score is just harmonic mean of precision and recall. By harmonic mean, you'll just calculate harmonic mean by 1 by F1 score equal to 1 by precision plus 1 by recall. And then when you calculate value for this, I'm sorry for this, this should be this should be F1 score, not precision. Like, yep, I'll just, so I meant this should be F1 score. So this would be F1 score, and F1 score value is 2 into precision into recall divided over precision plus recall. If you use this formula, you'll get F1 score. F1 score is nothing but it's like it's a balance between precision and recall. For few models, precision can be too high and recall is 0. So there can be models which only detects positives but couldn't detect negatives. In that case, your precision will be 1 and recall will be 0, right? So for that, F1 score will be different. What if model will only be able to predict negatives, but it's not able to predict positives? So in that case, recall will be more and precision will be less. So there should be a balance in between, right? There should be a model should have a balance in falsely predicting something as positive or negative. So that's why we use F1 score. F1 score is something like if F1 score is close to 1, the model is good. If F1 score is close to 0, the model is like very bad, worst case scenario. Like 0 is the worst case scenario and 1 is a best case scenario. So if you have precision as 1 and recall as 1, that will be 2 over 2, that will be 1. So you for a model to have precision as 1 and recall as 1, there should not be any false positives or false negatives. So that should be like 100% accurate. That model, like whenever you pass something, that should predict the same actual label as predicted label. Then only F1 score 1 is possible, but it's highly unlikely given that the like you can't generalize any model for the entire data that's there, right? And also if you see this visualization here, if you start with 0 and 0, F1 will be 0. As you increase the precision and recall, F1 score keeps increasing, right? Okay. The next metric is ROC curve. ROC curve is also called as receiver operating characteristic curve. So the metric is you need to calculate the area under this curve. So if you take this square box, the area of this is 1 multiplied by 1. That will be 1. So that will be the metric. So in this case, the area under this curve is the ROC AUC metric. So this is also called as precision recall curve. So how we plot this curve is you just need to plot true positive rate versus false positive rate. True positive rate is nothing but TP over actual positives. False positive rate is nothing but false positives over actual negatives. So that's all with classification metrics. Let's move on to regression metrics. Before I start, do we have any questions, Chanika and Gunika?
We have some around multi-class classification, but I think we can cover that at the end.
Okay.
Also, I think some people are feeling that it's getting a little confusing, but yeah, there's no need to memorize all of these at once right now. Like the best way will be to, whenever you encounter the metrics, to come back to this video and try to understand what the speaker was trying to convey. Just sit back and listen and try to understand and gather as much as possible, but no need to memorize or worry if you're not able to understand anything.
Yeah. Okay. So let me just move on to the notebook and then show you some of these things. Let me. Okay. So I've actually taken an end-to-end example here. Maybe like before you get confused, I'll just start with the notebook and then like I'll show you how the things are getting calculated. So we have taken an example here where we have to predict whether the person has liver disease or not. So you have age of the patient and gender of the patient, and then there are some bilirubin related features. So you have all these features, and then you, based on these features, you have to decide whether a person is infected or not, right? So let's actually, I have actually done some pre-processing. Like I have loaded the data here, and using pandas I have loaded the data, and I have done some basic EDA, like I have seen the data and then like which format. Age is in numeric format, right? But the gender is written in strings, female and male. So as you already know, system can't understand strings, so you need to convert this as numbers. Like you can assign female to 0 and male to 1, like that. So that you have to convert this column as 0 and 1s, and like that if you have any textual column or string column, you need to convert all those columns to numeric values, so that your future matrix or your future data frame will only have the numeric values, and we can use it for training. So you can, I've just checked the columns. So columns, I have age, gender, and whatever columns I have showed you before, I have all these columns here. And when you see info, it just gives you the count of all not nullable objects, not nullable so not non-null objects. So we have 583 rows here for age, and then here if you see this column right here, this has 579 non-null values, but it has 4 null values, right? Because this count is for non-nulls only. Whatever is not null, it's showing that. So here I have 4 nulls here, so I need to take care. Either I need to drop those data points, or I need to fill that with fill those missing values, right? So I have done that as well. Here if you see, I've taken the same column and I have filled it with mean. Mean is like the most average, the ratio. I'm taking the average ratio of the entire column, and then like I'm taking that mean, and then I'm filling. So I've actually checked here. If it is null, just show me. Like if that albumin globulin ratio is null, we are selecting that, and then this here has missing values. So you need to impute these missing values here. So here when you miss those values, either you can use pandas, or you can just use scikit-learn's simple imputer, but you have to mention the strategy there. Strategy is mean. Here if you want to do it in pandas, you can do it. If you want to do it in scikit-learn, you can do it that as well, but you just need to import that simple imputer, and then like you need to fit your data into that simple imputer using strategy as mean. And I have done some basic pre-processing where I've already told you I need to change the gender, right? I need to change the gender as 1 and 0. So there are two types of encodings again. There are label encoding and one-hot encoding. Label encoding is nothing but keeping one column like gender and then giving two values, 0 and 1 here. So one-hot encoding is like how many our classes are there in gender, it will create that many columns. Like for female there will be one column, and for male one column, and then like if it is true, that will be 1. So here if this data point is female, the first one, so here if you take one hot encoding, it will be 1 and 0, because you have two columns for female and male. Female will be 1. If this is male, male will be 1. So all these, out of these 5 records, the below 4 are male, and only the top record is for female. In label encoding, you will have only one column called gender, and you will have values for, like, if you decide 1 for female and 0 for male, you will have ones and zeros like this, right? Even if you have three columns like male, female, and trans, like you will have in label encoding, you will have gender will have values of 1, 2, 3. In one hot encoding, you will have 3 columns like gender female, gender male, and gender trans male, and whatever is true is like a boolean value. Whatever is true, that column will be 1. Like in this case, if the first record is trans, so this gender female will be 0, gender male will be 0, and gender trans will be 1. That is one hot encoding, and that's the difference between one hot encoding and label encoding. And also you need to drop the target variable from the future set, because you won't pass target variable. Your target variable is liver disease, right? So you won't pass this to train the data. So you need to drop the target variable first, and then like you need to assign the target variable to something like y, and then this x is feature set and y is prediction set, and we split the data. So when you split the data here, so you will use test train split method from scikit-learn's model selection module. So in this, you just need to pass the feature set, the target set, and the test size. Test size, if you mention 0.2, 20% of the data is allocated to test data, and 80% of the data is allocated to train data. And random state is mentioned to get repeatable results. It's like if you don't mention random state, what happens is that it keeps shuffling. If there are 100 points, like if you don't mention any random state, you can get any 80 points in the. If you do it multiple times, you need to get repeatable results, right? To get repeatable results, suppose if you are creating a model, and then like you have split the data, then when you calculate accuracy, it was coming 80. But if you don't mention the random state, and then like when you try to train the model again, you might not get 80%, you might get some 60%. Maybe because the values are shuffled, the same training data which you used, that is not there now. But if you use random state, whatever the train data you have used before, even if you run it multiple times, it will generate the same train set and test set. And the stratify I have used to create class imbalance, to create class balance between test set and train set. Let me just reiterate what I just said. So if you use stratify, it will make sure that you have all classes in train and test. So if you don't mention stratify equal to y, when it divides the data into train and test, I can have, like in test data, there can only be one class, and it can be so let's take dog and cat example. So in that case, when you split the data, test set can only have dogs. So in that case, it's not good to use the test data, right? Because you are not even testing the cat's data. So when you mention stratify equal to y, it makes sure that cats and dogs are there in test, cats and dogs are there in train. But if you don't mention this stratify equal to this target variable, what happens is that 20% might not even have cats. If you have heavy imbalance, like if you have 90% of the data as dogs and 10% of the data as cats, like let's take this scenario where like 90%, like out of 100 examples, 90 examples are dog and 10 examples are cat. And when you do this test train split, I need to make sure that test data has both labels, cat and dogs. So the best way to do is to use stratify option here. I hope I'm clear with this. And we'll just create a baseline model. Like there is one classifier called random forest classifier. Random forest classifier is like tree-based classifier where you take different samples of the data in different subtrees, and on that subtree you will actually create subsamples of futures, and then like each subtree is like a model in itself. Like it tries to learn something based on the conditions. Suppose if like let's take one example, like if gender is more than 60, he probably might have like liver disease. And then it's like a conditional thing, like based on one condition it gets assigned to another one class. And if you get another condition, it might get assigned to another class. It's like that. So I have imported that random forest classifier. It's part of ensemble package in sklearn. And I have initialized the classifier, and I have fit the data. Like I started training the data, and with train features, and with feature data and target variable. So here, once the training is done, you will try to predict the values, right? In prediction, you pass the test data. Like here, this is training. Like if you see, this is training step where you use dot fit method on the classifier, and this is testing step. Like when you test it, you just use dot predict function. Mostly you'll be using dot fit and dot predict most of the times to train and test. Here, if you use dot predict and then pass test data, that will be your predictions. So here there is a method called classification report, which is like a summary of how good that classification is. You just need to pass true variables, like actual values and predicted values here. Y test is the actual value, Y prediction is the predicted values. So here, when you do that classification report, it just gives you a nice info like this, where this is class 0, right? Class 0 is I think class 0 is here. You can see class 0. There should be like 1 should be assigned to, yeah, here 1 is he has liver disease, 0 means he doesn't have liver disease. So let's consider 1 as positive, and 0 as negative. 1 is positive and 0 as negative. So I've covered this. So here when you see this, you will have precision recall F1 score for all classes. Like we have two classes, positive class and negative class, and precision should be there. Precision recall F1 score is, as I already told you, class related metrics. So this will be there for the negative class and positive class as well. So you need to have a balance between these two. You can't just have like a very value close to 0, like 0.1 or 0.2 for 0 class, and then here 0.9 for 1 class, because you need to strike a balance between detecting positives and negatives. You like the model is not good if it is only predicting positives and ignoring negatives. And also it depends on your use case, right? Suppose if you want to use the fraudulent transactions data set, you should be more focusing on false false negatives, not false negatives. You should be focusing on finding the fraudulent transaction. Like telling the normal transaction as normal is less important than fraudulent transaction as fraudulent. I hope I'm clear. Like your model should be able to say a fraudulent transaction as fraudulent, but um, it can be less accurate in telling a normal transaction as a normal one. Because what we are trying to do is we are trying to create a model which detects fraudulent transactions, right? So predicting a normal as normal, that is sensitivity, right? So your that is sensitivity, so that can be less. So here, this is the confusion matrix which I have showed in the PPT. So you have a nice module, you have a nice method called plot confusion matrix. This is there in latest scikit-learn only, so make sure that you update your scikit-learn to latest version. Otherwise you have to write the whole method to draw this. So import you just need to import that method, and then you pass the estimator random forest classifier, and the test data, the future set and the target set of test. So when you see this, these are true labels and these are predicted labels. So here if you see, if you take 0 as negative, these are true negatives and these are true positives. Like that, you can just associate, like you just need to map this with the figure in PPT, right? So here if you want to calculate accuracy, you just need to add up these two columns, which are yellow and green, 82 plus 62 divided by all these boxes, right? That will be your accuracy. Like suppose if you want to calculate precision for 0, that will be your precision for 0. We are calculating precision for 0, so that means we need to see zeros predicted as zeros. That will be 82, right? 82 divided over uh, predicted positives. Precision means actual positives by predicted positives, right? So this will be 82 over 82 plus 21. That will be your precision. So the same value will appear here. That will be your precision. And so there's actually a class imbalance in this data set. That's what I was wondering. So here if you see, you have the 416 positive patients and 167 negative patients. 416 people have the out of all the persons, 416 people have liver disease and 167 has doesn't have liver disease. So that means model has class imbalance, and model is having bias towards these positive patients. So this is actually dangerous, because most of the time, like, model might get more bias towards this class, and then like it only gives this class and it won't even like properly train the native class. So what we need to do is we need to fix this class imbalance before we do anything. Like, you can just create a basic model, baseline model, but you still have to deal with this class imbalance. It's very important to check the balance for classes. If you don't have balance for classes, things can go wrong. So just make sure that you just do this. You just check the counts of the target variable, and then just see whether there's a balance or not. So to create the balance, I'm actually using something called imb learn. This is a package where you can use it for sampling. So here I'm just taking when you take this random oversampler means oversampling the minority class. So when I meant majority class and minority class, majority class is the class which is dominating in the class. Like, that is class 1 here. If you see this, yeah, that is class 1. This will be class 1 will be your majority class, and class 0 will be your minority class. When you have majority and minority classes like that, either you can bump up the minority class by bump up the number of minority class. I'll explain that here itself. So either you can increase this 167 to 416, or you can decrease it 416 to 167. So, but decreasing is not a good option, because the more training data you have, the better model works. So what we can do is we can take the minority class, which is people not having liver disease, and then we'll oversample it to match this class. So oversampling means it doesn't do anything. It just selects random points from this 167 and then just replicates the points. Like it's like selecting random data points in this class and then just replicating it. When you do that, you will have the balance, right? 416 and 416. That's what I've done here. If you check here, so I'm actually printing the I have used this nice method called counter. So when you do this, it just gives you all the values of all the classes, like different values. So here if you see, I've used the random oversampler, and then I've used a random state to replicate the results again. And when you do this, you just need to fit the resample, like a fit resample. You just need to pass the x and y data. When you pass that, see, this is the original shape, which is of y, which is target variable. The original shape is, there are 416 class 1s and 167 class 0s. But after doing this, I have assigned this to y rows, right? So y ROS, if you see the counter, it is having 416 ones and 416 zeros. So that's pretty good. We have taken care of class imbalance. Now when you use train test split, everything will be good, right? So the data will be divided in between, like 80% and 80% train and 20% test. And Stratify also you have used. So you have made sure that test and train data has all the labels. So we are good to experiment with models now, since we have taken care of imbalance. So let's start experimenting with modeling. So I just taken random forest classifier again. Here, if you see, how much accuracy you have here, this is accuracy. You have 0.71 accuracy with class imbalance. This baseline model is before handling the class imbalance. Before handling the class imbalance, you have 0.7 accuracy. But I have taken care of class imbalance here in this step. Now I'm trying random forest classifier again. Let's see how it behaves, okay? So if you evaluate the model, if you use the same classification report method here, I got 0.86. How cool is that? If you check, sorry for that. So if you check here, like it drastically improved. Class imbalance takes like, when you take care of imbalancing, you can actually get very good results. So, and also once you use, you can, so in machine learning, we mostly follow this approach where like there is this theorem called no free lunch. It means none of the model works for all use cases. Suppose if I have used random forest classifier here, and then like it's not guaranteed that this random forest classifier will give good results for all the use cases. So what you have to do is, in machine learning, like you have to experiment a lot. A lot means a lot. You have to, in this random forest classifier, you keep changing these attributes, you keep experimenting, and then like you, until you get the better results, you have to keep experimenting. Like you have to keep doing future engineering, like creating new features and modifying features, and handling class imbalance. There are a lot of steps in pre-processing which can actually affect the accuracy. So there's a lot of experimentation involved. So even in this random forest classifier, you can do a lot of things. Like you can change a lot of attributes here. I've already told you random forest classifier is a tree based classifier. For any tree based classifier, what you will have, like you will have depth of the tree, which is number of levels, and the width of the tree, number of subtrees. Like a tree will have root. Under the root, it will have children. Each children is a subtree for the root node. So the number of subtrees are n estimators here, and the depth is max depth. So here, when you see this max depth, you can change this max depth to something else. Like you can keep experimenting with this. None means it can go until all leaf nodes are there. Like leaf nodes, as in, like none means there is no depth, there is no restriction for depth. It can go as long as it wants. And if you put max depth equal to 5, it will get restricted to 5 levels only. There will be only 5 levels. And also there will be like another thing called n estimators. N estimators 100. So this means there are 100 subtrees for a root node. For the random forest classifier, it's a tree. Like imagine it as a as a tree. When you have a root node, you will have 100 subtrees. Those are each subtree as an estimator. So n estimator is equal to 100. So what you can do is you can keep changing these two attributes, or like whatever, like you can change any of these attributes actually, but you need to know what it is. So what you are changing. So when you keep experimenting like this, there is high chance that you might get better results. If you don't experiment, you won't get good results, but there is always scope for improvement. So how do we evaluate this model? When you evaluate it, like you just use classification report. Let me just show you guys how to print other metrics also. Like we have talked about accuracy, right? Suppose if you don't want this classification report, you just want accuracy score, you just do this accuracy score, and then like when you will keep getting the suggestions like this. Y true is what? Y true is Y test, and Y true is Y test, and the predictions are this. I've directly used the method here. So the predictions are these. This rfc.predict will return predictions. So you can just pass this. This will print accuracy score. That's it. So here you will get the full score, not the rounded one. But the classification will round the accuracy score. Suppose if you want to compare, like the closely compare two values like 0.862 and 0.864, classification report will only give 0.86, but this accuracy score metric will actually give the will not round off the value. Also you can have methods like precision score, calculate the precision score. When you do this, so when you don't know how to use that method, I highly recommend using help function in Python. When you use help like this, it will actually tell you what arguments to give and what it returns. So when you do this, one sec, precision score. Okay, sorry, I need to do this before I do that. So what you can do is you have to import that metric, because these methods are not defined right anywhere. So you need to import it from scikit-learn, and then it works. So when you import it from sklearn.metrics, so then they should work. Okay, so here if you see, it tells you what arguments to pass and what it returns. So you just need to pass Y true and Y predictions. So the same thing over here. Let's just pass this. I hope I'm clear, Chanukya and Gumika. Like, are there any questions so far on the notebook?
No, it's all clear.
Great. Okay. Where am I? Okay. So this is your operation, right? And if you want to see recall, you just need to call recall score, but you need to import that before, and just need to do it. You can get the recall score, and also you can calculate. I told you about that area under the curve ROC, right? So that one is also can be used via, I think it's ROC AUC score. Yeah, ROC AUC score, and when you do this, it just prints that value, right? I hope I'm clear. And you can keep experimenting until you get good results. I mean, this is 0.86 is pretty good. So this ROC value, how you evaluate performance with this ROC value? If this ROC if this area under the curve is near to 1, that is ideal model. That's the best model. So like 0.75, more than anything above 0.75 is good. Anything above like 0.5 and 0.7 is pretty average, and anything less than 0.5 is not good. Like, I mean, these are just some threshold examples I'm giving. It doesn't mean that if you have like 0.75, you should not keep experimenting and then try to increase the value, but you should be able to maximize this area under the curve or F1 score. So if you take so you don't generally use accuracy, precision, or recall to compare the models. Suppose even if when you are participating in some datathons or in Kaggle competitions, so how they evaluate is that they evaluate classification ability based on either F1 score or precision or AUC curve, ROC AUC curve. So these two are the main metrics in comparing the models. So F1 score is used. I mean, you should not use. I mean, there's no rule like that. But when you have class imbalance, it's better to handle the imbalance and then calculate these metrics, because when you have this imbalance, these metrics will be like skewed. So I recommend handling the class imbalance first, then compare the models with F1 and AUC curve. And also I have used another model here, which is gradient boosting classifier. So there are multiple techniques to increase the performance of a model. Like so you might have heard about logistic regression, which is a basic classification model. Also you might have heard about support vector machines or neural networks. So all these models are pretty basic. And when you see these boosting models, what they do is they learn from weak learners. So these boosting classifiers are these kind of ensemble algorithms. What they do is they learn from the mistakes, and then they try not to repeat the mistake again in training the data, or like in modeling. So it won't repeat the same mistakes again and again. But if you take something like a basic model like um, normal decision tree classifier, it might make the same mistakes because it doesn't know that these weak learners are not working, we should not use this. It's still like it does a lot of extra computation, and which is not that effective. You have to leave weak learners and then start focusing in creating a strong learner.
Hi,
So that,
Raviraj.
yeah.
I think ensemble models might be a little too complex for this session, so maybe we can uh, move further.
Yeah, I mean, I don't need to explain I've just explained the intuition. Intuition is to remove the weak learners and then make a learner strong. So that will be like a powerful technique. And then these classifiers usually works better than the basic classifiers like logistic regression and SVM. And also, I actually told it's usually. I mean, most of the times, but sometimes in rare cases, a logistic regression might work well rather than a gradient boosting classifier. So that's what I told. No free lunch. So you have to try out everything. So here I have instantiated that model and then trained the data, and then I have checked the same classification report. It has given me some metrics, and I think it's better to go back to PPT once and then see where we are. I have covered all these metrics, I hope. So usually you won't calculate sensitivity or specificity most of the times, but just remember, sensitivity is just recall, and specificity is true negative rate, which is model's ability to detect negative as negative. That's it. To predict negative as negative. So we have covered these, and let's cover some regression metrics. And we are done with classification metrics now. So there are other metrics as well, but those metrics are like out of the scope now. Maybe like you can explore later. You can see what other metrics you have for classification. So for regression, you will have multiple metrics. So, but the prominent one is mean squared error or root mean squared error. So when you say mean squared error, so what happens in a regression problem is that it tries to draw a linear line between the data points. Like when you have a do we have any okay, fine. So when you draw a regression curve, so the difference between the predicted value and the actual value, suppose my model my actual label is, so suppose a model is predicting the age of a person based on the color, height, weight. All these can be attributes, right? You can guess the age of a person based on height, weight, and other features. Maybe the thing activities he does. So that those all can be features, and you are predicting the person's age. And the actual label, suppose for a data point the age is 10 and the model has predicted that he is 20. So that will be 10 minus 20 will be your error. So 10 will be your absolute error. And when you square it, what happens is that this whatever error you get, that gets enhanced. Like you will be giving more weight. So when a model is predicting 11 instead of 20, this will be 1 square, which is less. But when a model for a 10-year-old person, if the model is predicting as 20, that will be 10 minus 20, which is minus 10 square, which will be 100. So your error will be 100. So you know that your model is not performing well. But say if you have like if the model predicted him as 11, so 10 minus 11 square, that is 1, right? So this is actually summation of all data points. So this error will be there for each data point, and then you will calculate the sum of all these errors, all these squared errors, and then you divide it by the number of data points. That is actually the mean of squared error. Mean squared error means mean of squared error. So that will be your mean squared error. The intuition behind squaring is to make the large errors appear big. Suppose if a person is 10 and then the model is predicting it as 100, so that means it is 90 square. 90 square means something is very wrong about the model. But if you have 10 and 11, it can be bearable, right? That is 1 square. Like that, you have to this is called y hat, which is prediction. So this y hat should be as close as possible to y. Then your MSE will be less. So the less MSE is, the better the model is. The high MSE is the model. You have to keep experimenting and then make the model better. And root mean squared error. So why do we use root here? So we use root because particularly when large errors are like not decided, like when you have when you have that previous example predicting the 10-year-old boy as like 90-year-old or 80-year-old is something that's very wrong, right? So you will actually use RMSE in that case. Mostly we use RMSE because MSE is kind of directly squaring the value and then taking the average. But when you use root mean squared error, you will actually get the smaller value of the error, but still you will still be avoiding the large errors. And mean absolute error is the same. It's just the difference between the predicted value and the actual value and the averaging it. It's like mean absolute error. Like it doesn't care about which direction it is going, positive or negative, but it's just that you just need to calculate the average. And when this is used, mean absolute error, and when you use squared error. So this mean absolute error is used. So before explaining this, I just want to explain what an outlier is. An outlier is something like which is very off from the existing data. Like suppose if you have um, uh, the prediction values, all prediction values are between 50 and 60. Suddenly, like you get a prediction as 500, that is outlier. Outlier is nothing but an anomaly, like are not as expected. You are not expecting that value there. It should not be that high or that low. So when you have that outlier, what happens here is that this MAE will have less error when you have outlier. Take the actual age is 10 and the predicted age is 100, right? 100 is the outlier. 10 minus 100 will be 90. So that error will be less. But when you take squared error, what happens is that this 10 minus 100, 90 square, right? So this will be like propagated much, this will be like very high. So that if MSE, if the MSE error is very high, that means there can be that's an indication that there are a lot of outliers in the predictions. And if you want your model to be robust with outliers, robust as in like to be strong with the outliers. So this, you should use MAE. And if you don't care about outliers, and then if you don't want outliers in your predictions, you should be always using squared error. And also having outliers is not a good thing. So it's better to use mean squared error most of the times rather than absolute error. And also I said most of the times, like there are a few cases where mean absolute error is important. So I've already covered that. It's the same thing. So this I have already covered. For fraud detection, in a classification example, for a fraud detection, one second. Specificity should be more than sensitivity. That means you should be able to identify fraud detections as fraud. That is more important than identifying normal detections as normal. And also disease detection. In disease, what happens is that both are very important. If a person has a disease, you should tell them he has the disease. If a person doesn't have the disease, you should tell him he doesn't have the disease. This is very sensitive issue. It's like you can't tell a person that he is COVID positive and he is not, right? So in this case, specificity and sensitivity both are very important. And also for regression, there are techniques. So I just told the same thing. Penalizing means increase giving heavy weight to large errors. Penalizing means giving heavy weight. Like even if you get like a small error, when it will be more, right? So it should be as close as possible to the actual value. The predicted value should be as close as possible to the actual value. So that means your error should be as less as possible. Even if the error is a little big, it should be amplified and then it should be reflected in our metric. And also MSE penalizes outliers as well. Outlier is same thing again, but outlier is having large error, but outlier will be having large error, like the difference like 10 and 100. So that will be penalized. That means that gets amplified. 90, the difference is 90, and the 90 square is like 8100. That will be too much, right? Then you'll understand that something is very off about this model. And MAE is used when you don't want to penalize outliers. Like if you have an outlier, but you still want to you don't want to penalize it. That means you are still okay with having outliers around. So RMSE is used when large errors are undecided. And also good rule of thumb is that it's better to report all the metrics. You don't know, it's better to, since all these metrics are already provided in sklearn, you just need to create a custom method, like printing all metrics, or like custom code you can write, and then you can use that everywhere, like print classification report, print precision score recall. I mean, if you print classification report, you don't need to print precision recall and reference score separately. You just need to, most of the times you just need to print classification report and area under the ROC curve. And the evaluation techniques. So if you take these evaluation techniques, we actually use cross validation, because so in previous example we have seen we have only train and test. So in that case, what happens, the train data is only used to train the model and the test data is only used to test the model, but you are not validating the data during the training. So the idea of cross validation is that during the training, just validate the model and then improvise it by changing the parameters. So like take that random forest classifier for example, and then I'm cross validating it during the training itself. So I can divide the training data set into 3 or 4 sets, and then I can use 3 data sets as train. So let me just show you in this. So cross validation has 2 types: k-fold cross validation and leave one out cross validation. In this case, what happens is that, so you will basically divide the data into 3 parts. Since k equal to 3, you will divide the data into 3 parts, and these 2 parts you will use it as test, and this one part you will use it for testing during the training itself. This is not the final testing, final evaluation. You won't be calculating any metrics as such here. But what happens here is that, since you are using a testing data set, since you are using a portion of training data set as testing data set, it will be able to analyze the performance. It will see whether during the training, it will see whether the model is performing well or not. If it is performing, if it is not performing well, it will go back and change the parameters, or like I mean, you can do that. You basically have to do that, change the parameters. But when you do cross validation, you will get your each data will be passing through training once. So what happens is that here in threefold cross validation, there will be 3 iterations. So in first iteration, this portion will be used for testing and these two will be used for training. In second iteration, this portion will be used for testing and the other two are for training. The same thing happens here. So in this case, if you observe, what happens is that each data point is getting tested and trained. That's a good thing, right? And also leave one out is same, but it's just that you will be using only one data point as testing and all others as training. Like in the next iteration, there will be a total of k-1 iterations, like not k-1 data. If there are n data points, there will be n iterations here in leave one out cross validation. So this leave one out is computationally expensive because you will be running a lot of iterations of training. So that's why it is usually used in smaller data sets, but it gives best results. And also k-fold cross validation is kind of leave one out, but it is like more of you won't take a single data point and then test it separately. You will take a collection of data points and then test it. And then in the next iteration, you will again take another set of data points and then test it. So that's about cross validation. No need to worry about that much. Like you won't be doing it manually. Most of the methods in scikit-learn provide cross validation feature. You just need to mention what's the k value. If you mention k value, then it takes that many iterations to train the model. So hyperparameter tuning. Why do we do hyperparameter tuning? To improvise a model. Like suppose if you take let's go back to the notebook. I think that should be better. So I'll explain it here. So hyperparameter tuning is used to tune the parameters. If you take random forest tree, for example, so here I've already told you the max depth and the n estimators. So you can actually keep manually experimenting with it. I can change it to 150 and then see how it is performing on the data. I can change it to 200, but manually changing these values is very tiring, right? You can't do it because there can be multiple parameters, and then like manually changing will take a lot of time. So if you want to see what parameters can be tuned, you just need to call getHead. So that will give you all trainable parameters. So these are all the parameters. So out of this, I can actually use these. You should be able to know. Sorry, you should be knowing what this attribute is accepting. So this bootstrap might be accepting a Boolean value, true or false, and also this class weight is a class weight might be a fraction, none or 0.1, 0.2, 0.3, like that, and criterion has different strings. So to see this, it's better to look at the help function. When you see the help, so you'll be getting all the parameters and what they are. So you have to read that and then see what can be changed to improve the model, right? So here if you see, it will clearly explain about all the attributes. So if you see here, max depth, right? Max depth says integer or none. So you have to pass only integers or none to the max depth. If you pass anything else, it will fail. Like criterion. Criterion is like string. So you have to pass this Gini string or any other string, right? So it's the same thing with n estimators. N estimators is integer. So you have to pass only integer, and the default value is 100. So make sure that you use this help function, because it will help you. You can just learn a lot in scikit-learn by using this help function. Like you can just take any method or any object and then pass it through help, and then read the user guide. That will help you learn more about that estimator or that method. So here I have just in hyperparameter tuning, so I have defined a custom method which actually prints me the scores, like mean of the. So since I'm doing cross validation, it trains the model 5 times. If I give CV equal to 5, it does the cross validation 5 times, and then when you get the 5 metrics, you need to calculate the mean of it, right? So if you get, when you do this, and then when you mention cross validation as 5, you will get 5 accuracy scores and 5 F1 scores. So it's better to take average of that, and then give the whole value to assess the performance of the model. So here I'm just calculating the mean and standard deviation of the. I'm just trying to see the distribution of the test score. That's it. So here I have used one classifier called gradient boosting classifier, which comes from ensemble algorithms. You don't need to understand completely like how it works, but you just need to understand that these boosting algorithms works better than the nominal classification algorithms. So I have used this gradient boosting classifier, and then in this I have you need to mention a parameter grid like this. After instantiating the model, you just need to mention the parameter grid like this, like the attribute and the possible values. Not possible values, these are the values which you want to try. So I want to try 5, 50, 100, 150 and 250. In this, so what happens is that it will try each and every value. So in max depth, I've given all these max depths. So if you remember, we have seen in the help section that max depth accepts integer or none value. So I'm passing all of them, and the learning rate. So how, like, learning rate is the speed of learning. So that also you can mention the values like this. So there are two types of hyperparameter tunings. Like we use two types of methods. One is randomized search CV and another is grid search CV. So first we're going to see what randomized search CV is. Randomized search CV is nothing but, so you will have a grid here, right? Parameter, this is called parameter grid. So what are the number of possible combinations? So any option will have a set of 3 parameters, right? Any model will have a set of these 3, like 5 to 0.03 or like 5, 3, 0.1. So you choose one from here, one from here, and one from here. So what are the possible number of combinations? So here we have 5, and here we have 7. 5 7 is 35, and 35 multiplied by 4, which is 140. 35, yeah, which is 140. So there will be 140 possible scenarios. When you try to execute this, imagine if you have a large data, like usually you won't like if you work with the large data sets, and then if you are running it for 140 times, what happens? Like it will keep on looping, and then like it will take a lot of time, and then it is computationally expensive as well. So that's why we choose to use randomized search CV. Randomized search CV, what it does is it randomly selects a pair, like a pair as in like it randomly selects a set of attributes and then checks. So if that is not performing well, and then it will actually randomly select, and then like it reports the values, and then if it's working better, you are lucky, and if it's not, then you have to try other values. But mostly it gives the optimal. It doesn't give the best values, but it gives the next to best. So it's like if you mention a number of iterations as 5, what do you think happens? Like I have given cross validation as 5 and number of iterations as 5. So what happens is that it will only out of all the 140 combinations, it will only execute 5 sets of parameters, because I have limited the number of iterations. So it has only taken 5 iterations to report the optimum value. Like it should be more than 0.8 the accuracy, but it was less because we didn't try many options. So here let me go to number of iterations and then increase it to 10. So when you do this, it will execute 10 sets of parameters, and then it will train 10 times. So this you can see the better value, right? Because you have tried multiple values. So if you keep experimenting, there is high chances that you improve this accuracy. Like first, what you have to do is you have to use the plain model without any hyperparameter tuning, like this one above, like this one above, and then see how much accuracy it is reporting. And then before going on to any other classifier and then implementing it, you try to make this classifier better. So to do that, you need to do hyperparameter tuning. So when you do hyperparameter tuning, you will pass these values which you want to try, and then you'll do this randomized search CV. What it does is it randomly selects the set of points and then executes it, and this n iterations is controlled. Like if you want to get good results, you keep increasing the n iterations. That's it. So that will give you good values. So I usually recommend this method. What happens is that okay, before explaining that method, I'll explain grid set CV as well. So this will be your this print results is the method which I have written. So this is printing like this. The best parameters are these. So out of all these parameters, 150 estimators is better, and max depth is 4, and learning rate is 3. So these parameters gave the best result, right? So how do you access this model? Like if you want to see this model, you just need to call rs dot best estimator. If you call this best estimator, it gives you the estimated value. It prints the estimator. And also if you call best score, it just gives you the best score, which is 0.8615. Also you can just do this best params. So it will just give you the best parameters. So that's about it. Let's discuss about grid set CV. So idea is simple. Grid set CV is used to hyperparameter tune and try different combinations and then optimize the hyperparameters to improve the accuracy or performance of the model. So here what happens is that the same 140 combinations are like here. I think it should be less. Okay, the same combinations. Out of all these combinations, what grid set CV does is it will try out each and every possibility. Like it takes 80 estimators, and then it takes all these values and it takes all these values. So when you run this, it will usually take a lot of time because it runs all these combinations. So since I'm printing this, it is easy to see here. So here if you see 80, so it goes from here. Learning rate you have defined as 0.03, right? It has taken one learning rate and then implemented max depth of 2 first, and also then estimators. So each value is getting paid with each value in an estimators is getting paid with each and every value in max depth and learning rate. So all possible combinations are length of this multiplied by length of this multiplied by length of this. Imagine like if you have only 3 parameters here, but still it's taking this much time and running this many parameters. But imagine if you have some 10 parameters to hyper tune, and then like each is having 5. So that means you will have thousands of possible combinations, right? So it doesn't make sense to try all those thousands of possible combinations like this. So what I usually recommend is use the randomized search CV, try some iterations, like number of iterations as 20 or 30 or like even 40. get the best parameters here. So once you get the best parameters here, use these as reference and then pass the parameter grid of grid set CV. So I'll just explain that again. Suppose if you have n estimators as 150, so there is no point in passing 80 and 90 here, right? Because it's too less. Like you can just reduce this and then keep all these values, um, keep all these values close to 150, so that it's wise, right? Because that is giving it decent performance per randomized search CV, and it is like fast as well. You are just getting the reference parameters for grid search CV and use these parameters as reference, and then may and put an anchor like you for max depth it's like 4, right? I won't go to 32 or 64 here. I'll just um, I'll just make sure that these values oscillate anywhere between like 2 to 10, maybe like 2 to 10 or 2 to 20, like that. And the learning rate also here it is mentioned as 0.3, and just make sure that it is like close to 0.3. That's it. So like that you can decrease the options here for attributes, these hyperparameters, and once you have these values, your number of iterations will decrease, and then you will be trying out each and everything, each and every possible combination. And when you pass the cross validation equal to 5, it also generates, I mean it's one iteration over the complete training data set for each and every possible combination. So there's a lot going on here. Suppose if you have 100 possible combinations, and if you mention CV equal to 5, the training is happening 500 times. So for each possible combination, there will be one entire pass through the training data set, and then for each possible combination you will take the average of the metric and then report it. So here if you see, for this possible combination I have 5 scores, and then from those 5 scores I've calculated mean and standard deviation. So this will be like this is the mean of these 5 scores coming from this possible combination. So I hope I'm clear with hyperparameter tuning, and you will just call best score and best estimator separately, and then you don't directly need to um, so what I'm trying to say is, how do you predict the data? Suppose if you want to pass the test data, right, you just need to call cv dot, I mean the name might be little confusing, because like CV you have understood as cross validation, right? So I'll just change this parameter value. It's maybe like I'll call it grid. So you can just call grid dot fit, and then if you want to predict, you can just call grid dot predict, and then like since you have already have X test, you can do that. That will directly predict. Since you already fit the data, this grid will have the best estimator already. So that means when you call grid.predict, it just predicts the values with the best estimator available. So when you call this model.predict will actually use these parameters. Any doubts so far, Chanakya? Hello. Hello.
Hello.
Yeah, hi
Hello.
Chanik. I lost you for some time. I don't know what happened. Hello.
Hello, Ravi.
Yeah, can you hear me, Chanik? Yeah. Hello.
Hello.
Uh, that's Chanik. Yeah.
Yeah. Yeah, Ravi. Tell. Yeah. Okay. I think Gunika is joining in. Ravi, we are able to hear you. I think. Hello.
Okay. Sorry, Chanik. I was on mute. So I was asking. I'm done with the hands-on, and I'm done with the PPT as well.
Yeah.
I've explained what I want to cover, and I'm done with that. So I'm up for questions now.
Yeah. Sure. 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 Yeah. We can probably look for. So someone is asking how to use optimization research on gamification and learning.
Optimization research.
Yeah.
Um, what do
Also,
you mean by gamification and
yeah, maybe the question needs some more context. So before we take that, maybe Gunika has some questions. Gunika, can you?
Audible now?
Yeah, you're audible. Yeah.
Great. Yeah, we have some questions from this session. We can take them one by one. Okay, first, since we were talking about grid search CV recently, so can you explain the main difference between grid search and random search CV ones?
So the main difference is randomized search CV is not computationally expensive. So if you mention this, it randomly selects a pair of possible combinations. It will select a possible combination, and then like it will it will just stop at n iterations. If you mention 10, it will randomly select 10 combinations, and then it will give you the results. But if you do this n iter equal to 10 in grid search CV, what might happen is that it follows a procedure. Like it will take this 5, and then it will calculate all the possible combinations, and then it won't give you best results. But randomized search CV is good because it randomly selects a combination and then gives you the results. I mean, it might not be the best, but it's pretty decent. And then um, you can use that value to decide what to pass in grid search CV.
Yeah. Also, like someone asked if we can perform the cross validation separately, or is it uh, do we
Yeah,
need to perform it with grid search and random search only?
yes, you can actually you can actually use cross validation separately. So for that, I think you have to use cross val score. That will be part of Skellam metrics import. There's a metric called cross val score. So you have to use this. So I already told you to know how to use it. Just pass cross val score, or just hope the suggestion appears in collab. Yeah, so you just need to pass the number of validations and like how many cross validations. So that will be, is it disconnected? No.
Yeah, I think that's not a problem. So we basically can perform cross
Yeah.
validation separately as well.
So in this, for this cross validation, you just need to pass actual labels, and no, I think you should pass the training data and then the number of cross validations. So it will give you the cross validation score. Yeah, it can be performed separately rather than using it in Bitsat CV.
Yeah. Okay, we have
Yeah.
some questions. Is there a case where we would need to one-hot encode the target variable?
I think it is from, sorry, I taken the wrong wrong module. So this cross-val score is part of model selection. So this will be just this. You just import this and then see the help section and then how to use it, and then like you can just pass those values. You will get the cross-validation score separately. Yeah, Gunika, sorry to interrupt, but you can go
Yeah,
on to the
no
next question.
problem. Great. Yeah. So is there a case where we need to one-hot encode the target variable?
Mm, no, actually, you can use either of it, but label encoding is one hot encoding will have like more columns, and label encoding is a single column which is having different classes. But you can use either of it. Like you don't need like you don't need to there's no restriction on using the encoding techniques. You can go for any encoding technique.
Yeah, I think the question was more about if we do need to one-hot encode the target variable anytime or not. Like if we have the target variable as categorical.
Mhm.
So like
uh,
do we need to one-hot encode it?
No, in most of the cases, like one hot encoding is pretty much used in deep learning, and also you have to do one hot encoding most of the time so that the output is vectorized. So by vectorized, I meant like each label is a vector where the correct index will be one and the other are zero. Like so suppose three if I have three classes, so I can just mention if it is yellow RGB, like red, green, blue. Those are classes. So if it is red, I can just mention 0 here, 0 here, 0 here. So in most of the classes, in most of the deep learning algorithms, it will be it is even in the loss functions. When you use loss functions, so that will be using one hot encoding. So to match with those loss functions, you need to use one hot encoding. So you can use either of the things, but if something is not accepting that encoding, try to use another encoding and then get it done.
Hmm. Okay. So moving on to the regression metrics, if you
Mhm,
can explain the ROC AOC curve once again in detail,
mhm,
like
mhm.
people were confused about how we decide the threshold and what information it actually provides.
Okay, going back to the PPT, I'll just go to the ROCAC curve. So here the ROCAC curve is, so basically this characteristic is the rate of TPR versus FPR, true positive rate and true false positive rate. So this will be like you need to strike a balance between positive class and negative class. It's like model should not just predict positives and then fail to predict negatives. Our model should not just predict negatives and fail to get positives. If the threshold is here, I mean, if the curve is like this, that means model is predicting only positives. If the curve is at this point, model is predicting only negatives. And if this curve is here, I mean, that is the worst case scenario. But that means why? Because the the area under the curve is, if this curve is here, I mean, that means the curve is like this. So that's a the curve is like this, that is area will be zero. That means worst performance. So if the curve is like this, I mean, if the curve is like this, like a L shape, inverted L, and then here if it is like this, and then the area will be 0, here area will be 1. So this is the best case, this is the worst case. And the threshold should be a balance between TPRs and FPRs. So that balance should be somewhere like so your curve should be somewhere as a like a parabola here, like the area under curve should be somewhere around 0.9 to for it to become a good model. Does that
Yeah,
answer the question?
yeah, that does. Thanks. Okay, one more question that we had commonly was about the multi-class classification. Like
Mhm.
how exactly do we decide on the true negatives, true positives, etc. in such a case? If you can just
So I'll do one
Okay.
thing. I can just show you the confusion matrix for a multi-class algorithm. So maybe that will be, if I
Yeah,
have,
that'll be great.
so you just need to check this. You will have confusion, a lot of confusion matrices. So yeah, this will be the confusion matrix for a iris dataset. I guess this is iris dataset. Yeah. So setosa and vesicular and these are types of um, these are classes. So here, if you have if you see this, setosa is predicted as setosa, so that is true positive for setosa, right? This vesicolor is this, right? So this is predicted as vesicolor. So this, so what this confusion matrix means is that there are 13 examples where setosa is classified as setosa. There are 10 examples where vesicolor is correctly classified as vesicolor. But if you have the value 6 here, that means the true label is versicolor, but it actually got predicted as virginica, right? And when you calculate the accuracy, so that will be the sum of this diagonal divided by sum of all these values. If it is versicolor, suppose if you want to calculate precision for setosa, that will be the true positives of setosa will be set the value where setosa, actual setosa is being predicted as setosa, so that is 13, right? So your precision will be 13 by predicted positives of setosa. Predicted positives as in like these things, these are predicted positives. This is 13 plus 0 plus 0. So for setosa, precision will be 1. So like that, recall also, um, recall is true positives by actual positives, right? That will be 13 divided by 13 plus, these are actual positives of setosa, this row, 13 plus 0 plus 0, that will be 1. Am I
Yeah,
clear? Yeah.
yeah, that's a good example. Okay, for the last question, I think if you can go over the hyperparameter tuning code once, just very briefly.
Yeah, great. Okay. Mm-hmm.
Yeah, if you can just explain the hyperparameter tuning code, like just what, how, why are we taking these parameters and what is it doing?
So hyperparameter tuning is trying to improvise the model by trying out different possible combinations. So as I already explained this, so you need to see the what parameters can be optimized. So for that, I already told you, you just need to call this gbc.getparams. So that will give you the possible parameters, and out of that you need to choose what to optimize. So you can optimize this max depth, or you can optimize this n estimators. So you can try out different combinations in this. So for this model, this is one model, but you can try different models with max depth equal to 2 and max depth equal to 4, none, and then number of estimators. You can keep experimenting with these values, and then, so if hyperparameter tuning, that if grid set, imagine a place where random search CV and grid search CV is not there. In that case, what will you do? Like you, in that case, I have to create, instantiate another model, and then like in that, I would just do this. Like suppose if I don't have hyperparameter tuning, I have done, I have used the normal model here without with default values, and so these are default values. I didn't set any parameters here. These are default values. So in default values, max depth is 3. But I want to experiment. I want to improvise the model. So in that case, what will you do? You have to implement this again, and like to train it again, you just need to execute this piece of code again and then pass max depth in that. Like max depth equal to, so you just need to pass the max depth here. Max depth equal to 2, and another parameter, like you can just use an estimators. You can just pass it as 150. But this is very tiring, right? I can't just do it all the day. Like I can't, if I have 140 combinations, I don't want to do this for 140 combinations and then evaluate it every time manually. So that's where grid set CV and random set CV comes plays a role. So here what we do is we just try out all these possible parameters. So these are the so you just instantiate the model, and then you pass all the values which you wanted to try for an estimators, and all the values which you wanted to try for max depth and learning rate. So if you use randomized search CV, it will randomly select a combination and then gives the results. If you use a grid search CV, it will try out all the possible combinations. And random search CV is computationally not expensive, while grid search CV is.
Yeah. Also, like, how do we decide which of the parameters we want to try out? Like, you've taken n estimators, max depth, and learning rate here. So,
Uh-huh.
someone asked, like, how do we exactly decide which of the parameters to try?
So to do that, you need to have a little intuition about the model. So without having any intuition, you can't just go to a attribute and then change it just like that. So by intuition,
Yeah.
I mean, suppose let's take a small example. I'll take logistic regression. Yeah, so I'll take logistic regression. So in logistic regression, what parameters you can change? So if you know the concept of regularizing the model, so there's a regularization term called C. So you can change that. So if the model is getting overfit, then what you try to do is you regularize that model, and if it is underfit, you try to decrease the regularization. So if you have the at least a basic intuition about the model, then you need to know then you will know what parameters to modify. Since I know gradient boosting classifier is a tree based classifier, I've gone for unestimators, which are subtrees, and max depth, which is depth, and gradient boosting learner using weak learners, and then like it actually uses a learning rate. So since I know that from the intuition, I mean like how the model works, I use that. So if you don't have any idea about the model, what you can do is you can just search for like the intuition, how boosting classifier works, read it. Once you read it, you will understand how it works. Then what you can do is you can just call for help from sklearn, like help gradient boosting classifier. It actually gives a pretty nice info, like it it tells you what parameter is what for that particular gradient boosting classifier. So if you see this, but before doing that, you need to understand all the parameters, right? What you can do is you just need to call the help section, and here you will have all the values, like it will explain all the estimates. Like here you can see, right, these are all hyperparameters explained, like what is what, and what values it accepts, what is the default value, and what it is the minimum of samples required to split an internal node, and also like criterion, the criterion is what, like that gets defined here, and what's the default value. So you will be having a lot of info here. Just try to read it if you don't understand about any attribute, and then keep experimenting with it. So here if you see learning rate, you can just see like learning rate shrinks the contribution of each tree by learning rate. There is a trade-off between learning rate and estimate.
Yeah.
So I recommend doing this, but before you try anything, just try to get the intuition of the model. Before you use the model, try to get the intuition of how it works and how it learns that.
Yeah. That was actually a great suggestion. Okay. That's, I think, the end of the session. Thank you, Raj, for patiently handling all the queries and explaining all the concepts in such detail. And any last suggestions or motivation tips you want to give to all the participants of the bootcamp?
Yeah, Gunika. So I would recommend only one thing: just get your hands dirty. Without getting hands dirty, you won't learn much. So try when you have a simple data, like try all combinations and all models. Like you keep experimenting and keep doing pre-processing. So there is always a room for improvement. Just don't get satisfied with any metric, any accuracy metric or F1 score. whatever you get, try to like you are your own competitor. Like it's like if you get 90% of accuracy, don't stop at that. Try to achieve more. Try to hyper tune. Try to optimize the model. Try to change the way you send the data to model. Like you can do some feature engineering. You can create some new features, and then you can use those features in training. And also like you can handle the imbalance using IMB learn or any other statistical methods. So keep experimenting until you're satisfied. And also like if you keep experimenting, you will learn a lot. And yeah, keep learning. That's it.
Yeah, thanks. That was great. Okay, thank you everyone for joining for today's session. I think we all had a great learning experience. And yeah, we can end the stream now. Thank you. Bye bye.